Welcome everyone. In this video I am going to discuss about complex differentiability and Cauchy Reimann equations. First, let's look at the definition of the complex derivative. Um, Suppose that f is a complex function whose domain is a disk, open disk, centered at z equals a and radius r. And this is a complex valued function. Then we say that f is differentiable at z equals a if I can write this way, if this limit is existing. Exists, right? And if this limit is existing, if this limit exists, then we say f is differentiable at z equals a and f dash a is equal to limit h goes to 0 f a plus h minus f a of h. I think this is clear because you are using the similar definition in real analysis course also, right? Then let's move into the Cauchy Reimann equations. Right, Cauchy Reimann equations is one of the most important theorems in complex analysis because it says that if our complex function is differentiable at some point, then it holds Cauchy Reimann equations. And converse is not true, but under some conditions, converse is also true, but we have to add some other conditions also, right? So let's discuss about that later. First we will prove that how we can derive Cauchy Reimann equations by using the differentiability of a complex function. So suppose that f is a complex function defined on a disk centered at z equals a and radius r. This function is differentiable at z equals a, right? Now I know that differentiable at z equals a. Now I know my complex function f is differentiable at z equals a, right? Then dabba f over dabba x at z equals a is equal to minus I dabba f over dabba y at z equals a, right? The x and y denotes the real and imaginary parts of my complex variable. Let's go to the proof of this theorem. It is not a difficult proof. and this is my point A, this is my complex plane. Right. First I assume that H is real. H means this one, right? Because I know that limit H goes to 0, Fa plus H minus Fa over H. Because F is differentiable at Z equals A, this holds. Right. So H can be any complex number. Therefore, because H can approach to zero in many ways, so therefore I first let's suppose that H is real. Right. So and I'll take A as A1 plus IA2, where A1 is the real part of A and A2 is the imaginary part of complex number A. Right. Now what is F dash A? Limit H goes to 0, and if A plus H will be if A1 plus IA2 plus H. Now H is real number minus if A1 plus IA2 over H. Right. If I simplify this further, I can have if A1 plus H plus IA2 minus if A1 plus IA2 over H. Right. Now I'm going to do some tricky thing. That is, I am using the fact that I can view a complex function as a function of two variables. So I will explain that. Suppose that Z equals x plus iy, and if fz equals z square, then I can write this as x plus iy square. Then I will get x square minus y square plus I into 2xy. Actually, this is a function of x and y. Therefore, I can write this as f x comma y, because I is also a constant, right? Similarly, I can write this expression in this way. So the first part is fa1 plus h plus ia2. Therefore, I can view this function as a function of two variables minus f a1 a2 over simple h. Now, if you are familiar with partial derivatives, you can directly see what is happening here. So what is this expression? This is the partial derivative of function f with respect to a1 with evaluated at z equals a. This is equal to da by f over da by x evaluated at z equals a. I hope this part is clear, because I have changed my x variable and I had done nothing to y variable, right? So I will recall that fact from partial derivatives if you need. How we are going to define da by f over da by f order by x at some point x naught comma y naught. This is equal to limit h goes to 0 if x naught plus h y naught minus f x naught y naught over h. Right? This is the definition of partial derivative of function f with respect to x. Right? Similarly, I wrote I used that fact here. Right? Now next we are going to approach to a along y direction. Right? Previously I approached to a along x direction. Then we are going to approach to point a along y direction. Right. I'll copy that here. Right. Now instead of h, I'll use h prime. Now h prime equals ih, where h is real. Then h prime goes to 0 means h goes to 0. Right? So that means when h is approaching to 0, I am approaching to 0 along imaginary axis. Right? So when h prime is equal to ih, then a plus h prime or ih approaches to a right. Right. Now I know that my h prime is imaginary number, and now I am using the same fact. F dash a is equal to limit. Now instead of h, I'll write h prime goes to 0 if a plus h prime minus if a over h prime. And I know that h prime is equal to ih. I'm using that here. And also when h prime when h prime approaches to 0, that implies us h approaches to 0. H approaches to 0 if a plus ih minus if a over ih. It is approaching to 0, and a is a1 plus ia2, then this will become a2 plus h minus f a1 plus ia2. ih, right? Next I will take I out of my expression, and this will become 1 over I limit h goes to 0. And also I am using the fact that I can write this function as a function of two variables. So this is equal to a1 comma a2 plus h minus f a1 a2 over h, and 1 over I is equal to minus I if I multiply both sides by I, and this expression is equal to, this is the partial derivative of function f with respect to y evaluated at z equals a. Right? Now I obtained two expressions for derivative at z equals a by equating those two those values, I can have dabba f over dabba x z equals a is equal to minus I dabba f over dabba y at z equals a. Right. Now I proved the statement that I stated. Right. Now using this fact, I can obtain Cauchy Reimann equations. Right. Now I know that f is a complex valued function, and suppose therefore it has a real part and imaginary part. Therefore we can suppose f equals u plus iv, where u is a function of x and y and v is a function of x and y. Right. And I'm going to insert this f instead to this expression. Right. Then I can have dabba over dabba x u plus iv evaluated at z equals a is equal to minus I dabba over dabba y u plus iv evaluated at z equals a. Right. Then this will become dabba u over dabba x plus I dabba v over dabba x evaluated at z equals a is equal to minus I dabba u over dabba y plus I into dabba v over dabba y evaluated at z equals a. Right. So if I take right hand expression to the left hand, then I can have dabba u over dabba x minus dabba v over dabba y plus I dabba v over dabba x plus dabba u over dabba y evaluated at z equals a is going to be equal to 0. Right. So now I got expression where complex number is equal to 0. This is a complex number. If you evaluate this expression at z equals a, then it is equal to 0. Right. So complex number is any complex number is equal to 0 if and only if its real part, both of its real part and imaginary parts are equal to 0. Therefore by using that I can have two equations. First one is dabba u over dabba x equals dabba u over dabba x evaluated at z equals a is equal to dabba v over dabba y evaluated at z equals a, and dabba v over dabba x evaluated at z equals a is equal to minus dabba u over dabba y evaluated at z equals a. These two are called Cauchy Reimann equations. Cauchy Reimann equations. I hope you understood how I derived Cauchy Reimann equations by using the differentiability of a complex function. Right. And at the end I will introduce another small terminology, and that is entire functions. We say that a complex function is an entire function if that function is differentiable everywhere in the complex plane. So I'll write the definition. Fz is said to be an entire function if it is differentiable at every point in C. In other words, I can say if f is differentiable for every z in C, then f is an entire function. For examples, I can state f z equals e to the power z, and any polynomial is entire. That means if you consider some polynomial like this an zn plus a1 z plus a naught, where n is greater than or equal to 0, any polynomial is an entire function, right? So that implies us, if this function is entire, if any function is entire, then it satisfies Cauchy Reimann equations at every point in the complex plane. So let's say suppose you have some entire function, and if you find its partial derivatives at any point in the complex plane, then those partial derivatives will hold Cauchy Reimann equations. So that is the idea behind entire functions. So that is important definition, right? I hope that you understood what I mentioned in this video, and in the next video we will discuss about another interesting topic in complex analysis. Thank you for watching.